All right. Hello to all of you. This is going to be the first review lesson for a series of lessons. I don't know if I call them lessons, but review lessons, I suppose. A series of them that I plan to record to capture the big ideas of the student, common problems, and the formulas that I feel like there's. First unit, of course, is so the types of motion that we discuss. Kinematics of constant speed motion, acceleration. I guess there are those things that are possible category. I mean, they might have graphs of something that's not, that represents data that suggests that the object is not moving, and then you see, but technically those are three categories. Constant speed, again, remember, indicates that you back to the plus. But those aren't always the same. Because technically, I'm going to give it a rare example, but usually it is the same. But not necessarily. Depends on if the problem involves some sort of turning. When I say usually physics problems, they're referencing something going in a straight line. But if they're referencing something that's changing its direction, right, or going in a circular path like this, around circular motion, even if it's going along this curve at a constant speed, the velocity is not constant because that velocity vector is changing. Right? So remember. Remember that if a direction of motion changes or the speed changes, but as long as the direction changes, then it's not going, even if it's going at a constant speed, like around and around a rotary at 50 miles an hour, even though it's a constant speed, it's not considered constant velocity. So we have our kinematic formulas, we have graphs, we have common questions, questions that are asked from it. So for constant speed motion, the graphs, remember that we usually use X to describe symbol to describe the position, even in horizontal position. Usually Y to represent vertical motion up and down on the Y-axis. But a lot of AP doesn't seem to distinguish that. So if this was X versus T graph or constant speed motion, what would that graph look like? What if could be any of those. What if it was any of those would be constant speed, right? As long as the slope is constant, because remember that the slope of the position versus time graph is the velocity. The only thing that's constant in linear graph is the slope. It doesn't change regardless of where you live along the line or at the same speed. These values, the y-intercepts, of course, represent the initial position. So all of these different examples that I've created, they all start at different positions. These ones down below are starting at negative positions. They're shown in the fourth quadrant. The first quadrant are all positive positions, assuming there's some number line, and something's moving either right or left along this number line, with zero maybe somewhere in the middle, and positive positions on the right, negative positions on the left. this case, I know that these two are moving which way, right or left. These ones are moving left. E is to the left. How do I know that? Well, the slope is negative, right? If this is a negative slope, and the slope is the velocity, then that's indicating the velocity is negative, which we know is to the left. These ones are heading which way? These ones are heading to the right. How do we know that? They're opposite slopes. Argument. The slope is the velocity. The velocity is the slope is positive, the velocity is positive, and we know that to the right. There are again other differences that they're starting at different positions. And it's not to say that the other quadrants aren't valid. They are. How do we model that motion? Right. T plus NX. T is on our x-axis. T is on the x-axis. X is on the vertical axis, but I'm sure you're familiar with that. A little weird at first because you're used to seeing X on the horizontal axis and math class. So T is our variable. As it says, velocity is the slope of the graph. Points is delta x. Rise per run, delta x over delta c. Where you pick the 2 points, you get the same ratio of delta x. So technically, this is also another formula. D is delta x over delta t. Rate at which position changes. We're not in the model that I've written above. That's down. Then again, the y-intercept doesn't have to be 0. Let's say a function that's at the unit mark. Yeah. Y-intercept always represents your initial value. So we've got really two. Delta x, delta t. These are technical vectors. I did put the these are two equations so far. There are others, right? So how do we draw the x versus t like this? Found the slope is number 4, and that tells us that the speed is 4 meters per second velocity plus 4 meters per second. That tells us that it's going right. So if somebody told me to put that on a graph, versus time graph, that happens. At all points in time, the velocity is constant. These two are matched. If the slope is constant for the position versus time graph, the velocity, then the velocity versus time graph. How would the acceleration versus time graph, which we haven't talked about, it's something besides motion. Still, you have to know what is the acceleration of something that's moving at a constant speed. Accelerated means you're not moving at a constant speed. Could have said, what's the acceleration of something that's moving at a constant velocity? So that answer, not accelerating. Going at a constant speed, then its speed's not changing. Going at a constant velocity, then your speed and your direction are unchanging. So what would be acceleration versus time graph? A versus t. This one now over this. Or yeah, go on to my original one. Acceleration. Along with horizontal axis. Zero. Okay. Constant speed motion problem is usually that much. We have to solve or something, but remember that the other idea, which I think is more important, is that when you're going at a constant speed, more important, for moving equal distances, some fixed amount of time. Car going along, that this car is going the same physical distance second. 1 second of motion is another 1 second of motion. You know that in that same 1 second interval, it moves the same distance of 5 meters. Then we know it's at a constant speed. Something that's moving with a constant speed moves equal distances per second in different directions. Say that it has constant horizontal speed, that means it's moving equal distances per second in the horizontal direction. When you come to projectile motion, that can become confusing because now you have something go along moving vertically and horizontally simultaneously, and one of them is actually constant speed motion. But it could be moving vertically at a constant speed. That means the vertical distances, something like a rocket or something, upwards. Technically flying upwards at a constant speed and in equal amounts of time. The formulas and graphs that I just had on the board would model any of those. And specifically, what those speeds are would be input into the models, into the graphs, and into the equations that model those graphs. So that's constant speed motion. For constant acceleration, what we're indicating with constant acceleration is that the rate at which your speed increases is constant. The rate at your speed increases. So if you're gaining a certain amount of speed in the first second, and then gaining a certain amount of speed in the second second, and gaining a certain amount of speed in the third second, because your car is accelerating along the road into the gas. But you notice that in the first second, it gained 5 meters per second of speed, and in the second second, it gained 5 meters per second of speed, and in the third second, it gained another 5 meters per second of speed. So at t equals 3 seconds, it's actually got an instantaneous speed of 15 meters per second. Then we'd say it has a constant acceleration because it's gaining the same amount of speed each second. The rate at which the speed is increasing is constant, gaining the same amount each second. Okay? So that's considered constant, but constant acceleration. Can be in any direction, right? You could be accelerating upward, you could be accelerating downward. When we get to these laws, the direction of the acceleration depends on the direction of the net force. It's not always obvious, to be quite honest with you, right? If I drop a ball like this and say which direction is it accelerating, most people would say down. It's easy to think, hey, it's going down, down. Incorrect. But what if I throw this upwards? Now it's coasting upwards, 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 and I say which is the direction of the acceleration? Not as obvious. Well, with Newton's laws, which is the direction of the net force, while a ball is going up, 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 up. Free body diagram would show that there's only one force pointing down, so there's no air resistance. Therefore, if there's only one force pointing down, known as your weight, G, then the net force must be in which direction as the ball goes up, 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 up. Net force must be in the downward direction. Newton's second law says F net as a vector must be in the same direction as A, also a vector. F net equals ma. F net and A are both in the same direction always. So if the net force is down while the ball rises, that tells us the acceleration is actually down. It's always down, even if you're going up. Don't think that the acceleration has to be in the same direction of its motion. Certainly not, right? Your car is braking, your direction is moving forward because you're slamming on the brakes, you're still moving forward, but the net force left. The normal force up and the gravity force cancel, and the backwards forces from air resistance, friction, all those are backwards forces. The net force will be backwards while you move forward. That's why you're slowing down and decelerating. Again, another example that the acceleration is backwards even though you're moving forward. So in all of those cases, most of the time they're referencing constant accelerations or constant decelerations. Could be that you, as you slam on your brake, you're losing 5 meters per second of speed in the first second of skidding, and then in the next second of your skid, again, driving along and slamming the brakes. Each second, tenth of a second, doesn't matter what the interval is. The first tenth of a second, your car loses 5 meters per second of speed. In the second tenth of a second, your car loses another 5 meters per second of speed. In the third tenth of a second of the skid, your car loses another 5 meters per second of speed. You can say that's a constant acceleration again. Technically, I'd like to say deceleration. Textbooks are both speeding up and slowing down, just acceleration. We'll distinguish them with a plus or minus sign, and even that becomes confusing. You can't say, speeding up is always positive acceleration. Slowing down is always negative acceleration. We'll come back to that. But those are again things that you have to be aware of. That the accelerations can be direction. Sometimes it's obvious, sometimes it's not obvious. Constant, again, whether it's speeding up or slowing down, constant acceleration just means the thing is either gaining the same amount of speed per second, constant acceleration, or the thing is losing the same amount of speed per second while slowing down, constant deceleration. That's a constant. How would you know from a motion map that something is speeding up? Back in 9th grade physics, you would see that this car, as it moves along, starts off slow, and it's going faster, and it's going faster, and wow, it's really going fast. What's the key in that image for us to know that this thing is speeding up? But the distances are increasing each interval. So the first 0 seconds and 1 second, the first second you cover this distance, but in the next second, further. Next second, 2 and 3 seconds in video, if you watch this car drive past the road, we would know it's, or along the road, we would know it's accelerating. The fingerprint of acceleration is right there in the image. It's gaining speed, it's gaining distance each second. And that's what speed is. Speed is how far you go in a certain amount of time. And if how far you go in each second is getting bigger, then your speed must be getting bigger. Right? We call that acceleration. So that's a visual, again, for constant acceleration. What would it look like for deceleration? The car is braking. All of a sudden, at this point, the car jams on its brakes. It's moving at a big speed of 50 meters per second. It jams on its brakes, locks off its brakes. 1 second later, it's in a skid. Moving fast here, a little less fast here. Where will the next one be? Closer. Okay. And where will the next one be? Closer. Where will the next one be? Right up. The idea, the distance it covers each equal interval of time compared to time. As long as you pick some interval of time, like 0.1 seconds or 0.2 seconds, continue going forward that same interval of time in the video, if the distance is getting shorter and shorter, then you know for sure that thing is decelerating. You wouldn't necessarily know if it's a constant deceleration or if it's constant acceleration just from this image. You'd have to do some more science to tease that answer out. But that's just a general idea. And again, it doesn't matter if it's going up or down. Dropping the ball would be like this, right? For each interval of time, the ball would be covering a larger distance. So we dropped it from up here. distances vertically get larger and it's accelerating. In that case, we know for sure it's constant acceleration because that's what Newton's second law says. F net is equal to ma. If the net force is a constant number, an unchanging amount of unbalanced force known as the net force, then the acceleration must also be an unchanging number because F net equals ma. F net and a mirror each other. Mirror each other in direction. They also mirror each other in the sense that if F net is actually increasing as it moves, the acceleration will actually increase as it moves. If F net is actually decreasing as it moves, the acceleration will decrease as it moves. If F net is actually constant while it moves, the acceleration will be constant as it moves. Right? And for something that's falling, free-body diagram-wise, it's just one force. Doesn't matter whether it's going up or down. Just net force is down. Bottom line is it constant throughout the video? If you remove air, of course. Yes, it's always a downward force equal to what you weigh. For me, it's always 800 newtons. So that means the acceleration produced by my weight must be a constant. We call that G. Acceleration due to gravity for our plane. That's enough on that. Acceleration. What would all these look like graphically? Graphs come in here. Exam for sure. So what would my car example that I just drew? So the car, that starts off with a little bit of speed, and then all of a sudden it starts speeding up. Accelerated. What would the x versus t graph look like? This is where it started. We call that the exponential equal to 0. We call it the 0 meter mark. The initial starts no speed. Car starts itself. What would this graphically look like? Well, this distance is shorter than this distance, shorter than this distance. So on our x-axis, we're just mapping that out. Here's the first short distance. First interval of time gave us some small distance. Next one is further. Next one is next same interval of time. The next interval is further. Down on the car. Right. Measure, observation. What we have to move those over. You have to move those points over because we're plotting out that idea out. This was where it was after 0 is 0. This is where it was after 1 second. This is where it was after 2 seconds. This is where it was after 3 seconds. Here. Here. Could certainly draw a straight line through the first 2 points. See that those are definitely straight. Yes, straight back to math class. Which tells us that, again, modeling this motion versus time, and it's the formula has to have a square. What would that model look like? Well, the model still has to include constant speed motion. It has to incorporate constant speed motion plus something extra. Because we know if it was going at a constant, right, then that would be a straight line. This straight line would really be modeled by x initial plus b times 2. That's what defines this whole, all the data points that fall on this line. But that's assumed again constant. That would be the constant speed. So we know when the car is actually accelerating, which is what we're talking about, there's a little extra distance it covers, right? If you had two cars side by side, one of them is going at a constant speed, or the same car. The same car can either keep going at a speed of 5 meters per second, moving 5 meters forward every second, but in the next experiment, the car actually gains speed every second. Then after 3 seconds, let's say, if it was going at a constant speed, this would be the car. However, since it was accelerating in trial number 2, it's further ahead. Like we're looking down. This is the extra distance. That extra distance right there is equal to 1/2 h squared. It's equal to the extra distance the car travels, compared to where it would be if it was just moving at a constant speed the whole time. Since it is accelerating, it's gaining, it's comparatively again, comparing to itself, its own motion when moving at a constant speed, always has a little extra distance at 3 seconds, or at 4 seconds, or at 5 seconds. So you compare where it is in the accelerating scenario versus where it would be if we just moved. For that reason, we always assume that. That's what takes this model, of course, which is linear. Y equals speed. As soon as you add this, that changes things. You add a square term now. So that is the model. BI represents the initial velocity. Charting something's horizontal motion in the simple case of a car that's accelerating, or a runner, which they sometimes talk about on a track. They're accelerating. We call the horizontal axis that they're running or driving along the x-axis. X as a function of time, meaning their position somewhere along the race depends on t. That's what x is. X is their position depends on time. X is a dependent variable, t is an independent variable. Will be modeled by bam, right? Where did they start? That's x initial. Start at the 5 meter mark, then I have to note that and put 5 in for x initial. What was their initial speed? Runner starts at rest. Well, the initial x is 0, right? And then the runner accelerates at 3 meters per second squared. 3 for head. Or they say the runner's already running, and you start tracking the runner right as they go by you. They're already at their top speed, let's say, or already moving with some speed. And just as they pass you, you start your watch and you start tracking their position after they pass you. In that case, when you hit the timer, boom, right as they passed you, that's the first moment, t equals 0 seconds. Oh, their speed wasn't 0? They were already moving then? Yes, they were already moving with a speed of 13 meters per second. Then VI in this formula on the top right would be 13 meters per second. Always 0. A lot of problems it is 0, but not always. Decided to call where you were standing the 0 mark, then x initial would be 0. They say, no, the 0 mark was actually back there, and the person with a stopwatch was standing, 10 meters ahead. Well, okay, then I'd have to stick the number 10 in for x initial. Number 13, that was their speed as they passed that person that was standing, starting to track. So those things matter, whatever the acceleration is that we go in. Let me also point out, this becomes not. There might be problems where the x initial, like I was just doing. Let's just say x initial is 10 meters. The initial velocity is 13 meters, and the acceleration of the runner is 3 meters per second squared. What does this actual model that I have on the top right numerically look like? Then this is x plus 13t plus 1/2 times 3 times t squared. Then plus 13t plus 1.5 t squared. This is now the correct model for that particular graphing calculator. I can see the curve, and someone said extrapolate our data and predict exactly where the runner will be at t equals 17 seconds, assuming that all of these properties in terms of their initial speed, but assuming they stay at the same acceleration of 3 meters per second squared. Let's extrapolate, predict what their position is at whatever 27 seconds later. Well, you could just plug in 27 for t, formula that comes with it. Good. Perfect. You could go on a graphing calculator and graph it out. Go to graph and say x equals whatever I said, 27. X in that case is 2. It'll give you the answer and tell you this is where the person should be. It's a model. It's a model for the position of the person as a function of time. You don't use backwards direction because that's negative. The second one will be negative. All right, so that, and let me say one other thing. If they were to give you, because this is sometimes one of their questions, they give you this. This is the multiple choice question. And then they ask, so what is the, based on this model for the position versus time of this runner, what is the runner's acceleration? Choice A, 10. Choice B, 13. Choice C, 1.5. Choice D, 3. That's the kind of question they might ask. You have to make a connection between a numerical model and an abstract, just algebraic model, right? It's like, again, y equals mx plus b in math class. It's just a generic format. Y equals mx plus b is very closely related to the formula y of x equals 2 plus 5x, where you say, oh, b is 2 and 5 is m. You say, as an algebra teacher, that's right. We're sticking those numbers in, using our general model y equals mx plus b for those particular values. Very important for students to recognize that. Know the formula here, but this could become specific to any particular moving object. This can be a challenging question, which I'm posing again. Based on this, what is the acceleration? Most common wrong answer? 1.5. That's not correct. As we showed here, the coefficient is 1/2 times the acceleration. Right? 1/2 times the acceleration. That means this number that we'd like to just say, oh, 1.5 is the acceleration. That's not true. 1.5 is equal to 1/2 of the acceleration. Equal to 1/2. I multiply both sides by 2. Somewhere ahead, the acceleration check 3, which would say, oh yeah, that's what we started with, and this big problem we just made up. Be aware of that. It's the most difficult question. Usually, if you're going to ask this one, that's it. It's the most challenging one. It could be, what is the initial velocity of the runner? 13. That's the coefficient of the linear term. What's the initial position of the runner? 10. That's the only constant. Change with time is always changing. Middle one changes. At 2 seconds, that middle term is 26. At 3 seconds, that middle term is 39. Same thing can be said about the third term. Those are all changing terms. To compensate for the fact that this thing's position is changing, we need to keep increasing so that the overall output properly models the position of the runner at some given time. What is the most common form of this that you use? For an acceleration problem, where they say the initial position is 0, the runner starts off with 0 speed, or they're dropping a rock, and how far has it fallen after some amount of seconds? You can imagine dropping a rock. Why not? Just call that x equals 0, initial 0. Now let's fall from there. Just call it initial 0. You dropped it, all right, initial 0. Or again, it's the runner who starts off at the beginning of the race, starts off as x initial 0, starts off not running like all runners do. So they start off with speed, and again, the first term and the middle term are 0, and all you're left with is 1 half m squared. That is the most common usage of this formula, because many of their problems are, as I've described, relating to something that starts off at the 0 mark. Starts off at the 0 mark and doesn't have any issues. So usually I just write this fancy writing it as a T. Not really. I mean, a lot of times they want you just to know that if it's all starting at rest and starting at initial position 0, then the distance measured from there in the forward direction that it will travel in some amount of seconds t will be equal to 1/2 times whatever its acceleration rate is times t squared. So write down the model. That's it. Gets you the points. If something is falling at a constant acceleration, which free fall is always that case. Free fall, by the way, describes the motion of something falling only due to the force of gravity. That means it can't be air resistance, it can't be any other forces at play. All that's free fall. So if that's true, then there's no other forces, then the net force down is surely your weight, and therefore the acceleration would be g. That's how it happens. Right. So be aware again that A becomes G in free fall problem. The question: how long does it take to drop the ball from? How long does it take for the ball to fall from the top of my head to the ground if I hold out a ball and drop it straight down? So the distance is the meter Mr. Kurzak, which is h. And then we just ask what is the correct model for this time that it takes to fall to the ground. V is the acceleration it experiences while falling. T represents how many seconds it's falling for. And D or H represents the distance it will fall in those amount of seconds T. Right? We're asked to model that. Time to fall. Start with time to fall. The distance h from rest. It has to be from rest. If you decided to throw that thing down, the ball's in his hand, he throws it down with a certain speed, out of it leaving his hands, coming out of his hands as a speed of whatever, downward speed of 10 meters, 20 meters per second. Then the time to hit the ground is no longer modeled by this, because that middle term over here on the top right is now VI would have to be whatever, -20 if I threw it down. I now had h equals -20t minus 4.9 squared. I want to do that from G. If I solve this for T, it's certainly not going to look like what I have in the box. There's a term that screws that up. Maybe 22. Minus 0. Now you're in the ax squared plus bx plus c0 format, and then you know, graphing calculator to solve for the zeros, the x-intercepts. Yep. But very rarely again would that be the case. Usually, yeah, their problems simple. Let's start that at rest. This middle term is time. Therefore, algebra. All right, a couple other things. We know now that the x of t position formula is x. If plus position plus 1 half is clear. And we know that the graph is actually set. How about v? Well, remember, the velocity is the slope at any point on this graph. Slope of the tangent line at that point in time. So this is, I don't know, the 1 second mark that I just dashed. If I drew a tangent line there, then whatever the slope is of this tangent line represents the velocity at t equals 1 second. It represents the instantaneous velocity at 1 second. If I did that for 3 seconds, 3 second mark, and my vehicle is now over here. Slope is it's moving with a much greater velocity at 3 seconds than it was back here, which was 1 second. Slower, lower slope. Another idea, reminder, slope of the position versus time graph is the velocity even on a curved graph, right? That introduces you to calculus concepts. And now, if it looked like this, which it looks like for a ball that you throw straight up in the air, and track its motion as it goes all the way up and it comes back down, x versus t really. But notice this slope is less right at the top of this path. Slope is 0, which tells us that the speed is 0. It's at the top, acceleration is not 0. Acceleration is still negative 9 degrees downwards, even if it's not moving. And then the moment we go to the other side of this, those slopes are going to have negative slopes. Get steeper and steeper, indicating that it's now coming in the downward direction. Velocity is those slopes. If those slopes are tilted in the way I'm showing them here, those are negative slopes. The line goes like this, is negative slope. And the steeper and steeper is indicating that's gaining speed. And we know that it's falling, right? Negative direction. What would the model look for that look like? Again, for something that's, it's dropping something, dropping a rock, right? What would velocity versus time look like for a rock that's being dropped? Hold it out and drop it. Velocity versus time, assuming just falling, no air resistance. We know it starts off with no velocity, but which way would it go? All in a downward direction, and this velocity value would have to be reported as negative numbers or plus. That's what velocity versus time graph looks like for something. It's falling, it's been dropped from some height. Yeah? But on the other hand, if it was the runner that starts on the track and begins to accelerate at a constant rate, to the right. The blocks. 0. Velocity. Going to the right. These are all positive velocities. What does the slope of this represent? Between any 2 points. Is it delta v over delta t? Right, we're right. Delta v over delta t. That's acceleration. Technically, I will point out it's actually the average acceleration. Technically, put an average over that. Or if it's a constant acceleration, you take away the average, because what's the point of talking about an average if it never changes? You always get 80s on the exam, and y down. But if your grades change, then it makes sense to talk about the average. Point being that the formula for acceleration or average acceleration, average meaning, hey, as he ran, his acceleration itself was actually changing. What's his acceleration? Same rule. Do you have 2 points in time where you know his velocity? If so, then you can do V final minus V initial. V final is the second point, V initial is the first point. Do the delta V. Take the time that elapsed between those 2 points, divide it out. Whatever that answer comes out as, that's his average acceleration during that time period. If you say, oh, no, he was going at a constant acceleration the whole time. Same thing. Find out 2 of his speeds or velocities as he's running along the track. do a delta v, figure out what delta t is, hit enter, delta v divided by delta t, whatever comes out, that's his acceleration. We wouldn't say it's his average acceleration because it's, in this case, it's constant. If we take away that r, so what would model this? What would model the v of t graph? Really? So it should be in the form of y equals mx plus b, right? Where y is now v final, x is now x is not t. Axis. B describes y-intercept as the initial velocity. Now the slope, we said that here. Delta with a delta. Usually we would write that as the B final before B at B in which we range for. So you're right. That one worked here. So the one right here, one worked here. And we also now have okay. I'll make one other point. Now, if the acceleration was actually changing, this was a velocity versus time graph, and it was not linear like we saw before. This would be a constant acceleration, but it was something that had some slope that was actually changing. Someone said, what is between 0 seconds and this point right here? 4 seconds. What is the average acceleration? It's the average of all of these slopes. The average of all these instantaneous slopes is the tangent lines over this curve. To do that, all we do is draw a line from here to here, so that the average velocity in this area where it was curved, like this, so this acceleration was actually changing as we moved. The acceleration would still be calculated by using this triangle. The line that connects those 2 points right here would still be delta v, would still be delta t. Average slope between those 2 points, amazingly, is just the slope of the line that connects them. So, of course, find all of these slopes out here, so try to add them all up and divide by how many took, but you get the same answer as just doing the slope of the line that connects those 2 points. So you get something. So, lastly, I'll say the same thing could be said for B, or delta x over delta t. Something's not moving at constant speed, like this is you write average velocity. Same idea. Same formula, just like I have over here. The average, so the speed is actually changing, so we'll see, or the velocity is actually changing. So average velocity is still delta x, but delta x is the displacement. X2 minus x1, or x final minus x initial. And then the last thing I think on this is for constant acceleration, what does the acceleration versus the time? X versus t? B versus t? What would A versus t? It'd be like this. If it's a positive acceleration, but where would it be if it was a negative acceleration? which G, this would be the -128, shows the graph is showing where something's falling, free falling, what the acceleration of the graph would be. Like that there. Of course, this would also hurt. Right? Here's this T graph. It would look like either of those. An A versus T graph would look like either of these. An X versus T graph would technically some sort of curve. All right, I think I covered as best I could those concepts. In the next lesson, because I'm out of time, I'm going to go over the graphs in terms of the areas under the curves, area under V of T graph, area under T graph, I'm sorry, area under A of T graph, A versus area under V versus T graph. I think it's the only piece I can't squeeze in right now. Right. Then in the follow-up to that is projectile motion, 2D motion, especially where we'll focus on something that is very famous problem for people. Able check on that problem. All right, I hope that was useful to you guys.